We will have 5 sessions of maximum 20 minutes, probably 15. And if you have questions, write them down and raise your questions at the end of the 5 sessions. So put it down, know who will be raising the question to, and so at the end of the question, if you have questions, we make all the questions at the end. So Giulia, I give you the
Thank you so much. Thank you. Open. Thank you so much and welcome here. Welcome. Thank you for coming here and to listen at my presentation. Today we are going to talk about LEGOFIT and in particular the multi-phased LEGOFIT approach to tackling barriers towards the implementation of energy positive homes. Let me introduce myself. I'm Giulia de Aloysio. I'm a researcher, senior researcher and project manager at Certimac that is based in Italy. And today we are talking, discussing the different aspects we identified already in the project. Our agenda for today is divided into several points. In particular, we will start from an introduction of the project, then we will move on to the LEGOFIT approach. We will delve a bit into the LEGOFIT methodology, then we will talk about the barriers and drivers we identified towards the implementation of energy positive homes, and then we will draw up our conclusions. So let's start talking about LEGOFIT. What is LEGOFIT? LEGOFIT stands for Adaptable Technological Solution based on early design actions for the construction and renovation of energy positive homes. It is a project founded under the program Horizon, Cluster 5, and it is an innovation action. Our project will last 48 months. We are already at the 1 year after, and is led by the Turkish company Demir Energy, and we are 19 partners in our team. But what about LEGOFIT? What is the main aim of the project? Well, the main aim of the project is to design, implement, and validate an adaptable and dynamic, holistic approach to accomplish energy-positive homes based on a smart, innovative solution with high scalability and high replicability for efficient building, construction, and renovation. But what does it mean in practice? It means that we are going to develop a platform that is designed for professional and end users which has 3 main functionalities. First of all, it supports the decision-making process of the renovation and new construction. Then it aids the design process and it allows us to set up an innovative marketplace. Well, turning to our approach, to achieve our goals, we had 4 main pillars which underpin our process. First of all, we started to define the LEGOFIT APH. What do we understand for energy positive homes? To this, we revised the literature and we built on the definitions already present in the literature, and then we focused as an innovative aspect on the building's inherent bioclimatic performance. This is an innovative aspect that we are introducing in our project with respect to the existing literature definition. Then we came to a common understanding of the construction and renovation process phases. That is, we focused on the building renovation process because it's the most difficult, the most fragmented one, and we came up to a conclusion that we have 6 phases for each renovation and construction process in which and which stakeholders will contribute and how they are structured. Then we have started activating 5 pilots to demonstrate the LEGOFIT viability. We have 5 different countries to pilot our solution and to co-design our solution. Our pilots are located in Hungary, Luxembourg, Spain, the Netherlands, and Turkey. And last but not least, we have started setting up the LEGOFIT stakeholder community. That is the group of stakeholders who really are proactively involved in our project and will support us in the co-design of our solution. And we involved already target group, which belong to planning, renovation process phases, and also here we employed a multi-level approach based on 4 levels. But let's go into the detail of our challenge. Well, accomplishing energy positive homes is a very complicated task. And this is because we have the big barrier is the fragmentation, because renovation processes and construction processes are really fragmented, data, information, professionals, and so on. And this fragmentation is really compounded by the lack of awareness of people in the benefits of sustainable homes or long-term benefits of implementation of APH. It means that this leads to several consequences, like the resistance to change, to the adoption really of energy positive homes. These results, in view of this, we have a need to devise a comprehensive methodology that allow us to design proactive planning intervention and also to engage effectively stakeholders. To this end, we adopted a methodology structured into 4 main steps. In particular, we started to set up the framework, that is which is the environment in which we are moving, in which we are studying implementing our project. And then after setting up the framework, we started collecting the data, and this process was carried out in 2 ways. First of all, we revised the literature, and then we also had collaborative mapping workshop via Miro board with pilot leaders to ask them their contribution to profile the barriers and drivers in each country. Then we, after this kind of data collection, we analyze the data, and this phase of analysis already started during the collaborative workshop, because during the collaborative workshop, all the pilot leaders allowed us to analyze the data, and also after the workshop. Then after that, we validate and refine the method and our results. This is a sketch of our co-creation collaborative process. Here, this collaborative process with pilot leaders allowed us to collect real marketplace, share ideas, and understand how to collect suggestions to exploit barriers, to tackle barriers, and also exploit drivers. Going to depth of our methodology, we have several criteria to analyze the barriers. First of all, we thought about the type of barriers that we are experiencing in each country, that is technical, regulatory, social, and description. And then we focused on the description of the barrier. For example, that is which kind of barrier do we have, and its potential impact. Then we identified the pilot countries where the barrier occurs. After that, we focused on the stakeholder impact, where we identified stakeholders affected by or contributing to the barriers, because the stakeholders also contribute to the barrier. And then we had also the opportunity to identify the project phase where the barrier occurs. After that, we focused on the LEGOFIT contribution. How can we solve the barrier? Because it is not only important to say, okay, we have a problem, but we should try to find a little bit a solution, okay? And then we also focus on the project type. That is it a major renovation, or is it a deep renovation process? Is a renovation or a new construction process? What's going on? Allow me, please, to elaborate a little bit on the barriers. First of all, we focus on the technical barriers. We observed in our discussions, in our exchange, that there is lack of innovation, and this is due to, for example, to lack of skills, lack of skilled professionals. So how can we contribute to tackle this kind of problem? Well, we can enhance innovation by, for example, introducing and strengthening the BIM environments, introducing the digital twin, and also leveraging on targeted training programs, and also improving collaboration amongst the stakeholders via the LEGOFIT stakeholder community, and also on the open innovation community, that is the community of the professional involved in the construction sector in each country. After that, we focus also on the regulatory barriers. In particular, we can provide suggestion and recommendation on how to improve existing regulation via demonstration from real-world implementation. Our pilots are instrumental to do this. And then we can also promote the reuse of materials, for example, the recycle and reuse via the introduction of our material passport and the circular building passport. After that, we also have the ambition to try to tackle the financial barriers, the financial problems, because without money we cannot afford any renovation or any construction process. And how do we try to do this? By exploiting already existing successful models, business models, like the one we have in our country partner Spain from EOS Energy, that is like an ESCO model, and then also leveraging on crowdfunding campaigns. And then the social barriers. This is the most interesting one, I think, from my point of view, from my perspective, because if we are part of the problems towards decarbonization, we are also part of the solution. And this is the key, because here we are going to develop a user-friendly platform that is used by end users and by professionals. We are developing resident-centered crowdfunding by encouraging the resident to be involved in the process. And also we have the opportunity to reduce the performance gap via real-time feedback by employing the POESI tool that is already a tool developed by our partner list and also here developed. And also the LEGOFIT stakeholder community. It comes here. Turning to the drivers, we employed the same criteria. Let's say we focus on the description of the drivers, then the pilot countries and the stakeholder impacts, as well as the phase of coherence of drivers, and also, of course, the LEGOFIT contribution, how LEGOFIT can exploit the drivers. Well, we focused on the regulatory drivers, and here there is a very important factor that can be leveraged, that is the introduction and the adoption of the APBD. That is in May this year, was adopted definitely, so we can leverage the adoption and the minimum energy performance standards. We can also leverage the enforced performance monitoring of buildings. We can also exploit the financial drivers by mitigating the impact of energy prices. Why? Because we are going to implement energy positive homes. So in this way we can promote energy efficiency home and mitigate impacts. We can support the ESG reporting requirements because we provide really quantifiable data on the environmental and social impact of energy positive homes via our passports. We can also exploit, as I told you before, the social drivers because we can leverage citizen engagement towards sustainability, our community, throughout our community. We can elevate sustainability in political discourse because our LEGOFIT stakeholder community involves not only the professionals, but also politicians at local level. So we can also strengthen this, the sustainability in the political discourse. Let me talk about our conclusion that can we draw up from our research. Well, the main conclusion is that renovation and construction are really fragmented process. It's an extremely fragmented landscape. It's a very, very complicated to contribute. So most of the barriers are substantial and systemic throughout the process. Most of the barriers are common to the pilot countries. And what I think is important are these 2 points, because the barriers which are already present in minor renovation process are significantly amplified in projects aimed at high energy efficiency targets. And also the barriers mainly affect the stakeholders who must undertake the renovation and construction process. This is the end user, the demand side, who must undertake the intervention. The ultimate ring of the chain is the most affected one. So in this extremely fragmented landscape, we can potentially contribute, because as I told you before, we are part of the problem, but we are also part of the solution. So how can we contribute? By offering tailored financial technical feasibility assessment for innovative solutions, and via our BIM environment, by creating confidence into the process, and by fostering effective communication throughout stakeholders. But what is most important is to provide a systemic approach to renovation and construction process, as was also underlined yesterday in the contribution of BPIE. The systemic approach is really instrumental to tackle barriers. In the same way, we can also exploit drivers of the construction and renovation process by systemic or methodological approach. It comes to yesterday, to our plenary session, increasing awareness about the benefits of APH and promoting an efficient use of resources. This is my presentation. Thank you so much for listening, for being here. And if there are any questions, they will be addressed at the end of the... Thank you.
For staying the time. Was not easy. Let's move.
Thank you. In case. Perfect. Yeah, I'll try to 15. Well, thank you very much for coming. I'm Harry Watt. I'm a PhD student from the University of Sheffield. My background's in structural engineering, so that's where I'm coming from with this presentation. I'm just running through the results of a paper I'm hoping to get published. It's been submitted last week, so it's currently up for review, but hopefully be out soon. But yes, I'm trying to assess the carbon cost of structural adaptability, and just to introduce what I mean by adaptability. I broadly see there's two philosophies in structural engineering to achieve low carbon design. Either lean design, which is the more sort of optimization side of trying to reduce the material going into the building to begin with. And this would be sort of thinking just of the first use and really designing it to the codes, the minimum requirements, which would be that sort of designing for 50 years. Design for adaptability could be the sort of flip side to this, which would be the thinking of the long term, considering alternate futures right from the start, maybe use change. And it might require a small upfront overinvestment of material, but to allow for longer term savings, which I see as sort of aligning with the circular economy. As a background, we're all familiar with these sort of numbers, 40% from the built environment for global carbon emissions. And this graph sort of showing that as we've successfully reducing and continue to reduce operational emissions, our embodied carbon is going to become more and more important and a higher component of the building's carbon emissions. So this graph, which we actually saw yesterday in the one of the opening sessions, showing the influence a structural engineer has, the opportunity, comparing it to flights or vegan diets. One way we can do this is obviously aligning with the circular economy, or familiar with that sort of broad description of keeping materials at the highest value for as long as possible, so keeping a building as a building, and if not, a beam as a beam, and then if not that, then at least steel as steel, not downcycling. And then there's three sort of axes of circular economy, which I think align with, we've got the narrowing resource flows, which links to the lean design, so that's reducing the material going in the first place. The closing resource flows, that more typical circular economy style, is maybe that design for deconstruction and reuse. But then design for adaptability comes in with this sort of prolonging the life of the building and that slowing the resource flows, slowing the flow from input to output. So the hypothesis of my PhD is that whilst lean design can reduce upfront embodied carbon emissions, design for adaptability will achieve greater long-term carbon emissions. So I'm wanting to try and find out whether that is true or not. Drawing that graphically, I prefer to see it this way. We have an increased step up for that initial construction for the design for adaptability line. But hopefully what that allows us to do is either avoid the need for maintenance and refurbishment, or if it is still needed, it'll be a much less invasive and lower carbon renovation. And ultimately, avoid having to demolish the building, avoid the obsolescence, and then result, therefore, in a longer term, lower carbon. But the question I'm trying to answer in this paper is that first step of what is that step up between the lean design and the adaptability? What is that overinvestment that we require? So to do this, I looked at 4 different design strategies that you'd, design parameters you have to think of when you're specifying a building in sort of 2 broad categories of adaptability strategies. The first being this reserve capacity, the idea that if we over-design our structures to begin with, they have more sort of fat in them to allow them to accommodate changes. So one aspect of that is the load you're designing the building for. If we over-design that, we can allow for changes of use more readily. That'd be the imposed load. There's also the serviceability requirements and the sort of the vibration limit. How sensitive is the building to inputs, rhythmic loading like walking around? How much does the building respond? And the requirements for that change quite a lot depending on what the building is used for. And then the other aspect of adaptability is that open layouts. How big is the space? And both in the vertical arrangement and sort of by story height, and then also in the horizontal direction, the grid arrangement, so the distance between the columns, the distance the beams need to span. So both those aspects dictate how open the space is and what the other the use options you have. Also the prestige of the building, how much the client might be able to charge rent on the building if it's perceived as a nice open space. So to assess these, I used a parametric modeling software tool called Panda that does concept level designs for buildings. And it has a few fixed inputs just to sort of limit the assessment boundaries. I only looked at steel structures. I didn't want the research to get distracted by a concrete versus steel debate. I just wanted to look at the adaptability. So just looked at steel, just looked at medium rise, 4-story structures. And then also the plan dimension of the building stayed the same. So we're normalizing the results over the same area. The way Panda deals with grid arrangement is you specify a minimum and maximum span, and then it divides that building dimension into an integer number of bays. So we can have, so the maximum number of bays is the plan dimension by min span, which kind of gives us grid arrangements that look like this. So here I've shown the 4 most extreme grid arrangements, the 6x6 being the smallest and the 12x12 being the biggest with the minimum and maximum I put in. And then you've got the, sort of the 2 most sort of thin rectangular. But there are also, or each iteration between that maximum number of bays and minimum number of bays in the 2 at the X and Y directions, which gives 100 unique different building layouts, building designs. Then the 3 other adaptability parameters were assessed by incrementally increasing the value input into the software. So doing a repeat run of all those 100 grids for imposed load between 1 and 8, vibration limit between 2 and 16, and then story height between 3 and 10. Once I do all those runs and get all that data, I can plot graphs for the material mass, the material required for those buildings, by that parameter increasing on the x-axis. Obviously, we're more interested in carbon, so I can do a fairly simple LCA methodology, just looking at the upfront carbon, because I'm just looking at that upfront cost at the moment. So just taking the A5 module input factors, so just essentially convert that y-axis to carbon rather than material mass. Alongside that, I wanted to try and evaluate what the actual adaptability benefit is of these imposed loads or these design parameters. What benefit are we getting? I was fairly sure it wasn't linear. There's not necessarily, you're not guaranteeing increase in adaptability by increasing your design parameter. And I'll go through some of those results in a minute. And the final step was to combine those 2 last plots to give this sort of non-physical number of adaptability per carbon. And what that allows us to do is to identify sort of optimum points along that parameter that maybe we're worth targeting, where we're getting the most adaptability for the carbon we're investing, but also identifying areas where we want to avoid, we're not getting any benefit, but we are maybe increasing the carbon cost. So to just run through some results, I've put up here the results for the mass versus imposed load for all of those 100 unique grid arrangements. We can see there's a general linear trend. As you increase imposed load, increase steel mass, not surprising. To help actually see the influence of the grid, I've just highlighted 5 grid arrangements. And then also I can convert that axis to carbon rather than mass by just using the LCA method. An interesting result, we still see that linear increase roughly, but we also see that the influence of grid arrangement, the increase of the 6x6 line is a much lower gradient than the 12x12, which sort of implies there's a higher embodied carbon cost for these larger grids than there is for the smaller grids. And what that shows is that the adaptability strategies can't be treated in isolation. Their costs compound, they don't just add. You have to sort of think about the whole picture of the building, not just the individual carbon cost for the strategies. Looking to the vibration limits, we get a similar positive relationship, but this time it looks more parabolic. And we also notice that the larger grid arrangement lines are cut short at higher vibration limits. And this is because the method used in Panda to use sort of simple structural sections and fixed floor plate means it can't find designs that work at those high grids and high vibration limits. In reality, we'd probably be able to think of options of making bespoke custom beam sections or maybe increasing the mass of the floor to increase the damping. But pretty much both of those options would almost certainly guarantee more material. So what I've sort of said is roughly we can extrapolate on that relationship we've seen before, at least indicatively, to get that almost parabolic relationship between vibration and carbon. The story height parameter looks similar to the imposed load, but actually, interestingly, rather than the lines diverging, they're converging. So the influence of grid is reversed. And a simple explanation for this is that a smaller grid has more columns. So if you extend, there's more columns to extend, more material needed. There's also an influence of whether the columns are failing by buckling or squashing, and that tends to happen more, that tend to buckle more for the smaller grids, and that buckling is more influenced by story height. So it's just a bit of a what's the governing design case coming through there. Yeah, see there. And the final one for the grid arrangement, I plotted it by average span along the x-axis. Obviously, we've got spans in both directions, so averaging out, and then those highlighted grids are just single data points along that line. What we can see here is a roughly, again, parabolic relationship. Interestingly, sort of a minima happening sort of somewhere between sort of 4.5 and 6, and actually a carbon penalty for going for very small grids. It's very unlikely to have grids lower than 4.5 anyway, but it's quite interesting to see that there's a good reason for that. There is no point trying to push the sector to go for even smaller grids. So just doing a side-by-side summary of those results, we can sort of see how they compare. And the vibration limit, again, as we thought, having a much stronger influence over carbon. Same with grid arrangement, and then there's also the impact of grid happening in the other parameters. And the imposed load and story height have a sort of roughly similar influence on carbon. Now, looking at the other side of the research was this adaptability scoring. So the way I produced the adaptability scoring for the imposed load parameter was taking the Eurocode defined load categories and the value they give for imposed load. I could plot these use types against their imposed load with adaptability potential as the y-axis, and almost draw a shape like that, sort of these stepped increases in potential, that as you increase an imposed load, you allow for more uses. And what that kind of roughly says is that adaptability potential is proportional to the number of uses allowed for by that load. What this method doesn't include, and I think a later iteration should, is the frequency or the commonality of that use type. This plot implies that an office is just as important as a museum or an art gallery, whereas actually the amount of offices we need should have a sway on that. And so maybe there should be a weighting which pushes up residential dwelling units and commercial offices. So we might actually see that the adaptability potential is pushed to lower imposed loads. We can do a similar thing for the other requirements. They're less codified, so some of them, especially story height, is less discrete and more of a continuous line. It's not as defined, it's more subjective. But with these and the carbon results, we can do that last step of dividing the adaptability by the carbon to produce these adaptability per carbon plots and highlight maybe the optimum areas and then also the areas to avoid. So yeah, these areas where we're getting the most return on our investment for our carbon, but also the areas where we shouldn't aim there. We should either reduce our imposed load to get to the optimum, or we may as well just put a little bit more carbon in to allow for a significant increase in adaptability. So just in conclusion, to summarize that, we've got the carbon cost. First of all, it's not necessarily linear. The cost for different parameters has different proportions, and the carbon costs of the different adaptability parameters, they combine and compound, not just add. With the adaptability scoring, we have the result that first of all, it's non-linear, but then also it's discontinuous. There are discrete step-up points in adaptability potential. And finally, we have this idea of this assessing this adaptability per carbon. It's sort of a theoretical concept, but a real good indicator that you could sort of take with you to design meetings, client meetings, and a way of visualizing discretely where you want to aim for along each of these parameter axes. But yeah, so that was a whistle-stop tour of the paper that's coming out hopefully soon. There's a QR code I've just put up there, which is to my paper that was published last year, which is more the literature review side and setting the scene for the research. And then, yeah, email, LinkedIn, and if you have any questions, either at the end or come and find me in breaks. Cool.
Thank you. And again, thank you also for staying the time. Perfect.
Nice.
Very nice.
Hello everybody, my name is Hrvoje Dorotic. I'm coming from the Energy Institute of Požar from Zagreb, Croatia. And today I would like to present you Horizon Europe project. It's called Uses for Heat. It has a relatively long name, but the idea of the project is to utilize large-scale seasonal thermal storage for green heat. So during this presentation, I will go through the different topics. First of all, I'll just briefly give you a snapshot what district heating is. I believe that everybody knows what it is here. I will give you a short introduction of the large seasonal thermal storage. I will show you how our Uses for Heat project comes in place. I will present you the most, I believe, interesting part of the project, and those are the demos, and bring it to conclusion. If you've ever been on such conference, you've probably seen some kind of diagram like this. It's actually presenting you the evolution of district heating through several generations. Officially, there are like 4 or 5 generations, and there are actually 2 the most important parameters which you can follow, which is the temperature levels in the network and temperature levels of the sources. First of all, you can see that the older generation is we have higher temperatures of the network, which actually also means a lower energy efficiency of the overall system. On this side, the older generations are fossil fuel boilers, fossil fuel generations, and as we are decreasing temperature of our networks, those more and more renewable and waste heat sources are becoming available to actually put in our network. And you can actually see as we are reducing the temperatures, we are increasing the number of potential sources. The biggest trick which is coming up is that those thermal sources and the thermal demand that we are actually want to cover are usually not same in the temporal distribution. This is visualization of this problem. You can actually see the blue line, which is following your demand. Of course, district heating has high demand during the winter season and low demand during the summer. Of course, this is just some base load domestic hot water and so on. The problem is you have some base units, so for example, waste incineration, geothermal energy, CHP, boilers and so on, and they are operable, which means they can offer base load. And there are some sources. The most significant one is of course solar, which we have a lot during the summer, but how to use it during the winter? Of course, the obvious solution is to store this excess, the green area shown in the diagram, use this excess of thermal energy, store it, and then use it during the peak loads during the winter season. For this, you need large-scale seasonal storage. So what are those? There are four most obvious technologies: tank storage, pit storage, and these two, which are important for us, are borehole thermal storage and aquifer thermal energy storage. Just to give you a short overview of what those are. Tank thermal storage is actually what you believe it is. It's just a big bucket of water, I mean huge bucket of water, stored underground, isolated, and it can be relatively large, but if you want to go to super sizes, you will use the pit thermal storage. Once again, this is a hole in the ground, which is hydrothermal insulated, and the thing is that with those two thermal storages, you can increase the temperature of the water inside, the thermal energy which is inside. The temperature can be in relatively high levels because of the materials which are being used. These two storages are actually utilizing existing infrastructure, that is the underground. These are using boreholes and these are using aquifers. So what are those? Borehole thermal storages are actually just a big bunch of boreholes put in the ground. And what is borehole? Borehole is actually really simple heat exchanger, which is U-type shaped. So the hot water is coming in, hot water is getting cooled down, the ground absorbs that heat, and colder water is coming out. You put those two in the series and in parallel. You have to model this. It's a relatively complex problem, but the geological engineers can do that. And you actually, your ground is becoming a big bucket of thermal energy, and you use the actual ground to store the thermal energy. There is no water in the ground here. However, you can use the underground water, which is called the aquifer. That's why the name is aquifer, the thermal storage. And here the problem is much more straightforward. Imagine that you have water temperature 10 to 15 degrees Celsius, and during winter season you are taking warm water, utilizing it in some kind of boosting device, usually heat pump, and this now cooled down water is getting into different aquifer called the cold aquifer. Now the catch is during summer season, you can utilize the cold aquifer for cooling, heat up that aquifer water and store it in the hot aquifer. So you have actually two aquifers which have to be separated, and then you can utilize both of them cyclically. This is probably the diagram which you also have seen if you have Googled seasonal thermal storage, and those are the prices per cubic meters. The most interesting ones are over here. Pit storages are these points over here, and you can notice that boreholes and aquifers are much cheaper, but per cubic meter of water equivalent. However, the thing is that the pit thermal storages are commercially available. They are, let's say, traditional solution, although they are not so often installed in the Europe. However, they have complex construction, but they have higher temperatures, which means they have higher energy density, and they can store more thermal energy than these two because of all the temperature regimes which are available in the ground. However, 80s and 80s are already utilizing existing infrastructure, and they are much cheaper per specific unit of water. However, they have lower energy density due to temperature regimes. These two are relatively more expensive per megawatt hour, and they are still in research phase, although they are already available in Europe in several countries. This is where actually our project uses for heat comes in place, where we want to demonstrate innovative large-scale seasonal thermal storage. Use for heat is Horizon Europe, which started in December last year, so now we are in the first year of the project. We are relatively a large consortium of 27 partners led by KTH from Sweden. We want to develop or innovate and make it more efficient and more cost effective these 6 technologies, such as drilling technologies, a groundwater heat pump, which you will see later on in the slides. We want to dig into collector pipes and solar thermal collectors and solar thermal panels. And of course, as probably every Horizon Europe project in last years, we want to develop AI-driven and big data models which will model and validate the demos, but also the replicators. We have 2 demo sites, so 2 pilots. One is in Oslo, Norway, in the neighborhood called Furuset, and the other one is Hrvoje Dorotic, sorry for this, in northern Italy. We also have 4 replicators, so Zagreb, Lom, Bulgaria, Lausanne in Greece, and Kvarnholmen in Sweden. I will be in charge for the modeling of the Zagreb replicator, which will hopefully be done in the following years. And now we will dig into the demo sites, I believe the most interesting part of the project for now. Oslo has a relatively large network. This span is around 20-30 kilometers. The main central district heating station is waste incineration site. And this transmission line is getting high temperature energy to different regions of Oslo, including the Furuset. The idea is that in Furuset, they want to have connection with high temperature district heating, and they want to shunt this thermal energy to lower temperature and put the low temperature district heating system. So the high temperature is around 90, for example, 95 depending on the season, and lower temperature systems around 50, 60 depending on the houses which have been built. The idea is that this excess of thermal energy which they have during the summer hours, they want to store it here in the borehole thermal field. So this is the actual snapshot. There is nothing here right now. So this is actually the green field investment which will be done. If we zoom in, the idea is that we have connection with district heating network, high temperature district heating network, connect with a technical thermal substation where we're going to have reduction of the temperature, and this excess of thermal energy during the summer season will be stored here in this borehole field, which is around 1 soccer field area. Currently, the designs are being put in place for these boreholes, and hopefully they will be finished in the upcoming months. Of course, the borehole is just at the heart of the Furuset demo site. Here we're going to have modeling done by Cartiv in terms of CAPEX, OPEX for the optimization of the system itself. Then we will have AI-driven model predicting control once the boreholes are put in place, and we will also utilize high-temperature thermal solar collectors in order to additionally charge the boreholes during the summer season. Riva del Garda in Italy is utilizing different thermal storage. It is utilizing the aquifer, and they have similar problem, but with a little bit of different solution. So once again, you can follow the blue demand line. Over here you can see high winter and low summer, and this red line is the technical limit of the CHP plant. You can actually notice that during the winter periods, they have to utilize their natural gas boilers to cover the peak. However, during the summer, they have problem because they have excess of thermal energy, and they are crushing the efficiency of the CHP so they can follow this demand. The obvious reason is just store this during summer to use in winter. Of course, this is not so easy to do. The idea is to do it by using aquifer thermal storage in combination with high temperature groundwater heat pump. It looks something like this. So you have CHP plant, which has production of thermal energy together with some condensator boilers, waste heat recovery boilers, producing thermal energy for the heating supply line, which is around 90 Celsius, so relatively high temperature. Going to the final customers, then you have return line, which is coming back around 65, and then you are reheating this return line once again to 90, and you are putting the whole system back in place. The idea is that they shut one of these boilers, waste heat recovery boilers, and they are utilizing this heat pump, which will boost the temperature of return, a line from 65 to 78 by using aquifer water as a thermal source. The idea is that you also have here a cyclical regime of operation. So during winter season, you have extraction of the thermal energy and using it for heating and storing it for the summer season. So the extraction is at around 38, injection is around 25, and during summer season, you are extracting this cold water for cooling and then heating up the aquifer water and storing it around 40 Celsius. The technical plans for this look something like this. So this is just one small part of the whole system, and I will just quickly go through it. So here you have a warm well, which is around 38. So this is the winter during the heating mode. You are cooling down this warm aquifer water from 38 to 95 and store it in the cold well. This thermal energy, which is being transferred in the second circuit, is used as a thermal source for the heat pump, and then you are heating this boosting the temperature of the return line from 65 to 80 and push it back into the district heating system. Ideally, COP will be around 3.14, and this still has to be validated once the demo starts operating. So this is the novelty. One of the novelties of the project is this actually high temperature groundwater heat pump. During cooling mode, so during summer season, you have the cold well, which firstly collects the thermal energy from photovoltaic thermal collectors, the collectors which are simultaneously producing electricity and thermal energy. First you collect this energy from the PVTs, and then you collect the excess of energy from district heating. So now you are cooling down supply from 90 to 65, and once again storing this warm aquifer in the warm aquifer water in the warm well for the winter season, so we have cyclical effect. One of the most important things is that those two aquifers are not allowed to mix, because you are not allowed to lose the efficiency of the overall process, because if you mix those two waters, then there is no cyclical effect of winter and summer seasons charging and discharging. According to the concept design, they do not mix because they're relatively far away. Yes, I'm just at the conclusion slide. So in this presentation, I briefly show you what we are doing in the project. The project is called Uses for Heat, where we are focusing on 80s and 80s designs. We have two demos. One is in Norway and one is in Italy. We are relatively early project stage. The final designs are to be completed soon, and the construction will begin, and hopefully by the end of 2025 we will have some of the parts of the pilots ready for data collection and ready for other project activities, and that is development of the energy models, which are based on CapEx OpEx optimization, where we're going to validate on the demos and replicators, which I will be in charge, and more on that on the next time, hopefully on the next presentation. Check our website and feel free to add me on LinkedIn, and thank you for your attention. I'm happy to discuss the project with you. Thank you.
Hello, everyone. Do you hear me well? Okay. So I seem to be the odd one in. I don't come from Europe. I mean, originally I'm from Europe, but I live in Montreal for 28 years now. And I come from the ETS, which is l'École de technologie supérieure in Montreal, and from a research group, which I will present in a minute. My presentation will be entitled Circularity through Modularity and Adaptability of Buildings. And I'm very happy to share these items with you today. So this is the name of our research group. It's GRID in French, but it's actually Groupe de recherche en intégration et développement durable, un environnement bâti, or Research Group in Integration and Sustainable Development for the built environment. These are the research topics of my colleagues and me. We have 4 professors in this research group, but we work a lot in collaboration with other professors from the other departments of the university. And as you can see, we cover quite a big, how to say, the topic range, starting from BIM and information lifecycle management through digital twins, construction industrialization and automation, and touching a lot to the legislation and regulations and contracts, because we found out that this is something that's not often discussed in our more technical, technological spheres, but it's very important. So collaboration, lean thinking, integration, it's something that should be also in the contract. And all this, of course, is done with an objective of sustainable development and circular economy. So I will present a very small fraction of these research topics, mainly around adaptability and design for adaptability, a bit around modularity and standardization and industrialization. And I'll finish with some future research items. So, of course, you know what a circular economy is, and just to remind one of the definitions, it's an economic system that uses a systemic approach to maintain a circular flow of resources by recovering, retaining, or adding to their value while contributing to sustainable development. And in each of the phases of a life cycle of a building, we should think about circularity, about how we can prolongate the life of a building, or how we can reuse items, components or assemblies of a building or civil infrastructure. Now, why adaptability? Some call it reversibility, and there is, I think, a terminological discussion that we can have around that. For me, it's adaptability, but I found very similar research done using reversibility. Anyways, that's for another moment. And what is the link to circular economy? So if we take this very known table of different strategies for circular economy, we can see that starting from linear economy strategies and ending with really circular economy strategies, the adaptability is really touching or covering the higher, so very efficient for circularity strategies. And that's why several of my graduate students concentrate on this topic and study it from different perspectives. So what is adaptability of buildings? It's the ability of the building to adapt to the changing needs of occupants, society, and the environment with minimal disruption to delay the end of the building's life cycle. And as you can see, these are some synonyms that are used. You will say flexibility, we'll say change, etc. But actually flexibility is more something that can be done right now, while adaptability looks further during the whole life cycle of a building. So we really are looking for minimal disruption. And what can be the reasons for change? They can be physical, just degradation of the physics of the building, functional, technological, environmental, economical, social, legal, cultural, etc. And we see that it really takes a shift in the culture, shift in the mindset, so that we can start thinking not about what is here now and how much we're going to invest, but what will happen with the building during all its life cycle, which might be decades or half a century, for example, from now. So that's really very difficult, especially for politicians, as we know. But let's look at designing adaptable buildings. I put here one of the main theoretical bases that you probably know. It's started by Brandt in '94 and then was developed by other researchers. And it talks about building layers or shearing layers. And they provide a way of thinking about the building that links both time and the building's material form, conceiving components as different layers of longevity. So here you can see the different lengths of life of the different layers as per Brandt. So if we try not to connect in a non-destructible way, in a destructible way, more to say, these components belonging to different layers, will not be able to have adaptable building. So these are some of the design strategies which can help us to reach adaptability during the life cycle of a building. So separate the building systems according to longevity, use dry mechanical connections, which leads to modular construction or industrialized building systems. Structurally decompose superskeleton and intelligent infill, open building concept, systemic multi-level grids, and open engineering systems. These are among others, of course. And here are some of the strategies of the typologies of adaptability, which are illustrated with an example. And theoretically, these were presented by various researchers with this circle, starting by adjustable, going through versatile, refitable, convertible, scalable, and finally movable building or elements. So these are the theoretical bases, and these are some of the prerequisites, as I already mentioned: dry mechanical connections, modularity and standardization of the interfaces, plug-and-play installations, so that they can be easily changed when needed during the life cycle of a building. And what about the business model? This brings really a possibility, a potential for a business model that we call Uberization of the construction industry, of the built environment, more to say. So here we have a building life cycle, and here the building is ready, it's being sold. But then it can need some refurbishment, it can need some adaptation, which can happen several times. And actually these adaptations can be done through a subscription model. So we subscribe, for example, for the interior of the building, and we don't demolish and throw out or recycle the materials, but we just give them back to the provider, who can give them to some other company to use them, or to some other household to use. And finally, when it's the end of the life cycle of the building, well, it will be deconstructed and recycled, etc. So this is something that starts to be explored, but is really not yet in the mindset of the industry, especially in Canada. I must always say that the context is Canada and mainly Quebec. So what is the awareness about building adaptability in our province? We did a small interview with selected people. It wasn't a wide scope interview. We really talked with people whom we know that they're interested in this topic from the industry, and they all said that they think about adaptability, but they don't use the same terminology. Usually they say change or renovation, and then when you dig deeper, it will come out as adaptability. What are the most frequent strategies mentioned by the participants? They usually, as you can see, they don't really do adaptability. They do more repairs, renovation, etc. So it's they have to shift. We have to shift as a society to the higher part of this table. What are the reasons which are provoking the need for change? Mainly functional reasons. So change the function of a building or a part of a building. And which layers are the most frequent to be changed? The services layers, of course, they might become, I don't know, broken, need to be repaired, etc. And the planification, the space plan. And finally, what are the most frequent strategies used? It's multifunctional spaces. So instead of adapting flexible functions and multifunctional spaces, so think about this multifunctionality possibility from the very beginning is something that's the most used by these professionals whom we spoke with. So we decided that it's about time to teach the industry about adaptability, and we started developing a framework for design of adaptable buildings. And how it got, in fact, what's the genesis of this proposed framework? It's based on the layers that I just showed and on the so-called design tactics that we found in this author's publications, and we actually enriched this with a lot of literature review. So that's it's actually a big Excel table for now, and of course I don't expect you to be able to read this, so I zoomed into part of it. So as you can see here, we have the layers and the sub-systems or sub-elements of these layers. We have an explanation because it's not straightforward. We have the references from which we took the explanation, so it's based on the literature, how the given strategy contributes to the circular economy, and then we found that there are two types of strategies. One type is to contributes to the prolonging the life of the building, and another type of strategies contributes to the ease of change. So these are always different and can be explained also. And this is a continuation of the table with this is the envelope or the planification, the spatial layer. Again, we have the same structure of the table, which is quite long. This project was done in collaboration with the CERIEC, which is Centre d'études et de recherche intersectorielle en économie circulaire. So it's a kind of a research institute which was created 2 years ago in Quebec. So how to measure or evaluate adaptability? If we want to have more adaptable buildings, can we look at the design and say, or look at the building and say, is it adaptable or not? So we were based on the same framework that you'll see in a minute, but we took into consideration the different types of measures that we can have. So discrete, yes, no, subjective, intangible, and quantitative, objectively measurable. We applied our framework, which was kind of customized to become with questions, and these questions have a best condition and the worst condition in the answers. So we applied this framework for evaluation to one building, which is a library and used to be a ballet school. So this is the form of the evaluation framework, which is actually really based on the previous framework that I showed you about the design of adaptable building. So this was the work of one of my PhD students, and we found also, looking through all these strategies, that the prerequisites, among others, are digitalization and industrialization. And what are the benefits of digitalization? They are the ones that you obviously know, but these two are kind of particular, that digitalization provides this information flow from the beginning of a design about the manufacturability and assemblability of a building, and also the digital thread of the information during building's life cycle. So if we designed an adaptable building, how does the user know that it's adaptable? We have to have this digital thread throughout the life cycle. And the other prerequisite, industrialization and prefabrication, about the mechanical connections, modularization, and simplified assembly and disassembly, eventually plug and play. Good. So a very quick view into another master's student's work around modularity and standardization and the potential of the industrialization of construction for adaptability. When we say standardization, usually people see boring and ugly buildings, but actually we can, if we start looking at the roses in Gothic cathedrals or even in Auguste Rodin's sculptures, we can see that actually he was prefabricating parts of the bodies of his figures, and this one is actually composed of 3 like that. So, I mean, you can be very creative and still use standardized and modularized elements, and this is the same example that I showed a minute ago with a company from Canada, which is providing this kind of modular elements for interior design. Now, my student looked into modularity, but with the idea of robotic fabrication. So then actually you don't really need to have the same modules as you can give to the robot to create whatever is in the model. And this is a framework she created for this kind of modular robotic fabrication in view of the future adaptability. So this is an application of this module, of this framework, and this is an example of part of a building wall which can become opaque or transparent depending on the needs, the functional needs in the two environments, on the two faces of the wall. And this actually touches to the kits of parts idea of the industrialized construction, where we have modules which can be combined. So this is a product development, and then the different projects can be just combinations, assemblies of these products. So this is something that will really facilitate adaptability of buildings. And future research, so this is the future of the first research I showed to you. So the framework, we want to decline it for different stakeholders so that it can become really like a usable guideline for designers and for public owners, for example. There is interest for that, so we continue the project. And then the digital thread. How do we indicate this in the digital environment, BIM-based probably, for the future use of the building? And finally, robotic fabrication, that's on the basis of another master student who already finished. This is discrete design of buildings, and again the modules can be fabricated by robotic fabrication, and yeah, we continue working, and these are the basic courses that we actually provide in a short program in BIM and digital innovations on master's level. So if you come to Quebec, Canada, you'll be welcome. Thank you very much.
don't know if I know the microphone. So that's the last presentation. So mine, I put me at the very end. It was not the plan, but okay. From all the previous presentations, they were all very different. Again, this one will be also very different angle of view. So we'll be speaking about testing and experimenting facilities and a project which is called sitcom.ai. And we will explain what we are doing in Luxembourg, but we have other testing and experimenting facilities. That was the end of your session. Okay, so this project, it's within the Digital Europe program. Quite a big project. It's a 40 million project that will last for 5 years. And the idea there is to support deployment of artificial intelligence in Europe. So what is a testing and experimenting facility? So that's knowledge, infrastructure, or competencies, some material that enable you to test AI solutions. So the idea is really that we speed the things because you don't have to build an IT infrastructure, you don't have to build data flows, you have everything there already on site, you get access to high-power computing if needed, and this is very under competencies in AI or machine learning also. So there are more than one, so this 40 million is replicated in different subjects. The one we are working is related to AI for the cities and communities. That's the one we are working on. There is also one related to agri-food, another one that is for industry, and the other one for health. So they are brother and sister of the project we are working on. So these are the countries involved in OTEF. And we are, of course, in the central one, as Luxembourg be there, and collaborating with University Gustave Eiffel in France, and IMEC in Belgium. And we are a list for the Luxembourg Institute of Science and Technology that you may know, hopefully. And we are working on this central node. We are, as Luxembourg, involved for electromobility. This is related to move, this one to power, so grid intelligence, these kind of things, and the connections, 5G, 6G, and so on. So Sitcom is really for supporting companies to bring AI solution to the cities and communities. And we are at least in the middle of this ecosystem. So what do we bring? Of course, we are the operator of the LuxTEF, this testing and experimenting facility in Luxembourg. And of course, we have already in-house everything which is related to the hardware, the software, the AI solution. It's there. We are using it for our daily job as researchers, some of us. And the idea there is that we provide it also to external people. That's really the basic idea. There are different components. Of course, as I said it, hardware components are there. We have also some software that is there and installed and running. We have cloud services that you can access to. And yeah, so that can give you, I don't know if I can show you the video. Probably yes. Not that easy. Oops. So this gives you an idea of the solution we speak about. We call it the visual, so that's a big visualization wall. That will be supported also by high-power computing that is on the background. It's really used to make decision support system. So we build some infrastructure, and we have the people that will go, we call it a tangible table. You will be able to simulate scenarios, discuss the scenario, change some parameters, see the impact. And the idea is that we can good discussion, but based on real data. So it's not that you have to make a decision for the city. We want you to make a decision will not go towards all the technical details of it. But if you are an IT guy, you will find some of the things there that are of interest for you. But globally, we provide the infrastructure. That's the message. We have also, within the framework, we are using a digital twin platform, and we already have quite a lot of data in there. But we do expect that probably if you come to us with problem to be solved with AI, probably you will also have some data that you will provide to us that will complement the data we have already in-house, and we will, with you, develop a pilot. And if it works, it becomes a commercial product that you will be delivering typically to the cities. Yeah, of course, there is all the normal scope for data analytics and AI. So everything, again, is there. We have also the experts. We don't, you may be very knowledgeable on AI or not. You may just be a private company with a good idea. You feel that probably AI may be a tool for solving the issue, but you are probably not even sure of it. And you come to us and we check it. That's a little the idea. Yeah, of course, we are, as a research center, we are very much embedded in the socio-economic of Luxembourg with partners. This is one of the cities we are working quite a lot with Differdange because they are part of the net zero cities, the 112 cities in Europe that will be net zero cities in, or should be, in 2035, I think. And we have little or bigger companies that's a charging point operator, for instance. We are also working with him to develop prototypes or products if it works well. So as a research and technology organization, we also think we have other values, the fact that we are neutral, for instance, toward the market. We use a lot data science, and we want to be impactful and also trustable. That's very important for us. So without going too much in detail, but that's a little the idea how it works. So you are a private company or even a research organization, and you want to deliver AI-based service to a city or community, for instance. So everything there in the middle is what we are providing so that you are able to test a pilot. And we do expect that if it works, after we are out of the game. That means the private company will work with an IT provider probably, use what we have developed in there, and we will provide the solution to the market. The idea also that the pilot we are developing, they should be available for all the companies in Europe. I will give some examples of some services. And that's one of the big points, because the company that come to us will develop a pilot, but the pilot will be given to everybody. So sometimes for them it's not a good business because they want to. So usually what we do, they will be 1 year before the other one. That's a little the message we say. So probably for 6 months, 1 year, we will not deliver the service. And they have this benefit. So we have services that we provide that are, we call them topical services. So they are linked to a topic, in this case, electromobility. And we have services that are transversal. They are generic services. You can apply them to whatever. Just some examples, for instance. The digital opportunity assessment for AI. You come with an ID, you have some data, you do think that AI may be a good solution, and we check it with you. We'll make 3 workshops to check it, to check if you have enough data, if AI is a good solution or not, because it may be that it's not AI, your solution, and we'll check that. And that's very short, and you get your response. Can my problem be solved with AI? Yes, no. If it's no, it's stop there. If it's yes, we have other steps that we can do. Or also we have what we call topical services. In this case, these are services linked to electromobility. For instance, we can do the charging occupancy optimizer. So you are a charging point operator. You come to us, say, I plan to develop 100 charging points in the city of Luxembourg. We'll provide you the best places for your charger. We will also say you how much power you will be delivering by saying the occupancy rate will be 45%, for instance. And we go also as far as giving you, if you change the pricing, we will let you know the impact. And you can see in some of the cases, okay, what if I divide my price by 2? I will get more people, sometimes not. And it doesn't change because the location is very particular. And they have also tested because they have deployed some charging points, especially in the north of Luxembourg. They are not used, or very, very little. And they are not used because it's in a rural area, and everybody which has an electric car in a house, they usually charge at home. So no interest for them to charge it at the supermarket or whatever. One of the other services, for instance, is also we have the vehicle integrated photovoltaic emulator. So there the scenario is typically you are public bus operator. In Luxembourg, probably your bus, or most of your new buses are electric. And we will make the simulation of what if I put solar panel on the roof of my bus. And we will, based on the real world, and the real weather in Luxembourg, based on 1 year, we'll say you exactly how many kilometers more you will be doing, what will be your benefit, if you have a return on investment, and we will calculate all that. So for the moment, we do it with TIS at École, the bus operator at École. Soon the service will be fully ready. We are still developing it for the moment. And that means that whichever bus provider in Europe can come to us, give the scenario, the timetable. We know the meteo for all the countries, of course, and we will calculate exactly the business case for the buses. So we do expect we develop it once, and it's available with a fixed cost. Yeah, maybe I don't go in each of them. This is one, for instance, that we use with Differdange. We can fully simulate not all the city, but close to, and be very precise in the fact that by simulating electric cars, charging point, the grid, solar exposure, if you put additional solar panel in the houses, we'll provide you exactly the impact on the grid. And we will also simulate the fact that you will have overload of the grid, or maybe underload of the grid. And we can really say that in this specific street there, you will have between 6 and 6:30 an issue in the evening. And we know exactly the issue. And so we just say, okay, and what if I put an additional solar panel? Or what if I put a battery in there? And we will, okay, battery is the solution, solar panel not, because it makes it worse, maybe. But we simulate it very precisely for the city. And after that, the city can decide to make investment, to provide incentive for solar panels, to ask to the grid provider to reinforce it, because in 2 years they will have a problem. So we are very, very precise in that, and that's a service we provide to the cities. Yeah, this is the one I was explaining for the buses and the fleet. It may be also things that buses. We see that, for instance, the food providers are a good candidate because they have also this the cooling system that is working constant, always, and so for them it may be a good solution. For the moment, for a lot of the solution, the benefit is not that high, but we know also that as soon as the solar panel will be better, we are ready to simulate it precisely. And probably if they are 5%, 10% more efficient, we start to have a very good scenario for the buses. Or sometimes you have buses that have a special line, and the bus is just missing some 50 kilometers of autonomy, not more. And maybe the solar panel are enough. Yes, that's something very different. We have fully energy lab where we can test the cars, the charging points, really in real environment. So we simulate totally the environment. We physically connect the car, the charging point, and we really test a lot of scenarios. We can also test if it's cool between minus 20, and if it becomes hot in 2 hours, what happens. We can simulate cyber attacks to the charging point, for instance, and that's real testing. Yeah? And we can also validate that you are interoperable, that you follow the standards, for instance, to exchange messages with the cars. We can simulate each brand. So, okay, let's make like it's a Model 3 or it's a Polestar, and you can simulate it precisely. So typically, this kind of service, these are the car operators that can come to us, or the charging point operator. Now we are changing our infrastructure so that even a truck will be able to enter in the lab and be tested. So it's as big as that. So yeah, I understand where our capex are going. Okay, this is, yeah, I explained it, optimizing the charger occupancy. Okay, this is also for the fleet so that we can precisely calculate the EV emission of the fleet. So I say precisely, it will be taken into account the reality of the grid at the moment. So you simulate your fleet, and we say, okay, on Sunday, today at 2, you are using 45% of solar energy or something else. And that's the reality, very close to. Okay, I did explain it already more or less. So these are the workshop, and I said the digital opportunity assessment. So we make a workshop, half a day, with you, and we end up with, okay, yes, you already have an initial POC, demonstrator, that you can check with us, and this is done in 2 weeks or something like that. And you understand what you can do with AI, and you say, yeah, very good, we can go further. Yeah, and that was it for me. So, yeah, if you want later on to contact us as list because you want to test something for AI, just send a message to this address or to myself. It works as well. So thanks for that. Are there any questions on one of the presentations? I have to check also if you have questions.
So you have in your system, I hope it was you, you have a poesy tool. What is that?
Thank you. I'm thinking about people who are online. Yeah. Okay, so can you hear me now properly? Yes, the Poesy tool is a web platform created by our partner list, who is based, which allow us to provide real-time feedback on the comfort in the building. So it's a very useful tool, and we are also developing some questionnaires for the pilot leaders in order to monitor the comfort in the indoor environment. Thank you.
Okay, very interesting. I'll continue the discussion about this with you.
Okay, and I had a question for you, because when I see I didn't see in your presentation the relative efficiency of this system to stock the energy between the middle of the year and probably the winter. Do you have an idea of the efficiency of the?
Efficiency in terms of thermal loss?
Yeah.
Thank you. So the thermal losses are dropping down with the size of the storage. The bigger the storage, the lower are the thermal losses. Depends on temperature regimes, but for example, for the pit storages, which are relatively high temperature, it's going around 5-6% yearly. So the amount of energy stored, the 5-6% is lost. But it's case-by-case basis. So, yeah, because of the huge volume, the ratio of the surface and the volume is good for you. So you are storing a lot and you have relatively small surface relative to volume to dissipate the heat. It's a case-by-case basis. It depends how long you charge, how fast, blah, 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 and a lot of things going on. Of course, the lower the temperatures, as in aquifers and boreholes, the lower temperatures. Yeah.
Okay, thank you. Any other questions? No? If not, I have to thank you all, especially the presenters, and also for each of you for